Welcome to qnawire.
So we are looking at a question regarding um, the estimate of um, the human body. We were given um, the value in pounds, and so now we're trying to determine how many atoms are present. So if we look at the chart that was given in our book, the whole purpose of this chart is to look at the human body and what it's composed of. And if you kind of read further in the textbook, you'll see that um, that the composition of the human body is actually very different from the Earth and the Earth's crust. And so when we go down and we look at table, I think it's 20.2, we see that the most abundant elements in the human body are oxygen, carbon, hydrogen, and nitrogen. So that's what we're going to focus on in our problem. And whenever you kind of break down these elements, it's apparently referred to as metallurgy, which is the process of getting a metal form of its ore. And so we're kind of just going to be breaking, it's a process of breaking down the composition of things, especially in regards to the human body. So now I'm just going to draw little man. And the problem mentioned that he's 150 pounds. So what we're going to do is the problem told us that we have 65% oxygen. We've got 18% carbon, and we have hydrogen at 10%. And the last element we're going to stop and use is the nitrogen, which is 3%. So from here, because this is the majority of what the molecule is made of, what we're going to do in order to get from pounds to the number of atoms, as the question is asking, we are going to have to convert. So 150 pounds is what we were given. And in order to convert, 1 pound is equal to 453.58 grams. So we also know that in order to get from grams to moles, so we've got to get to moles in order to eventually convert the moles to atoms. So what we're going to do is we're going to use the molar mass of all of these combined. So we know that all of these elements are diatomic, which means in their natural state, there's always going to be two. So when we look at our periodic table, we'll see that for just one of these oxygens is 16 grams per mole. But remember, oxygen is diatomic, so we're going to have 32 grams per mole. And for carbon, again, it's 14 grams per mole normally, but because it's diatomic, it's going to be, it's 12 grams per mole normally. So since it's diatomic, it will be 24 grams per mole because we have 2, so we're going to multiply 2 times 12 to get 24. And we get 24 grams per mole. And then for hydrogen, we're going to just kind of round it to 1, but because it's diatomic as well, we'll have 2 grams per mole. And for nitrogen, it's 14 grams per mole normally, but because it's diatomic, it's going to be 28 grams per mole. So when we total all of this, we end up with a number of 104 grams per mole. So I'm going to go on and put this in our dimensional analysis kind of graph. So I'm going to put this down here so we can go on and convert. So 104 grams per mole, or 104 grams, is equal to 1 mole of all of these substances together, their molar masses together. And now, in order to convert moles, so 1 mole is going to be equal to an atom of to this atom we're talking about, or the number of atoms. So in order to convert to atoms, we're going to use Avogadro's number, which is used to convert from pretty much any unit, especially moles. We normally use Avogadro's number to convert from moles to another unit that we're looking for. So today we are looking for atoms, the number of atoms. So we can make Avogadro's number any unit that we're looking for. So this would be in atoms. And if we do our full calculation, which means first multiplying all of these, multiplying 150 times 453.8 grams times 6.02 times 10 to the 23rd, and then dividing by 104 grams, we will end up with the number 3.94 times 10 to the 26th atoms. So that is our estimate of the number of atoms. Uh-oh. And now I'm just going to circle our answer, and this is our answer.